studied the voltage transfer characteristics of an inverter and seeing that how the bias or the input voltage result into the output voltage, which is complement. Let's take a look at widely used digital CMOS implementation of an inverter. So we use two MOSFETs in those devices. One is N MOSFET and other is a P MOSFET. And the body of both of these devices is connected to the source, so there are no body effects in there. And in this implementation, we get the actual concept translated into device. So we look at what happens in the operation of such an inverter circuit. We Let's take a look at two extreme cases, which is our high and low. And if you think about it, when the input it has logic low, which is 0 volt, and that will be now at this gate, the difference would be with this guy, and on this side would be difference with the ground. So in both cases at input low, and in the case of input equal to the power supply, what would be the situations on these two transistors. So now we are in this case we are taking the N channel device to be the driving transistor and the P channel device to be the load, which means that we look at the operation of one and see what happens to the other one. But it's a symmetric circuit, so it could be might as well reversed, and we get the same results. Now, let's see when the input voltage is equal to VDD, we can see that the gate voltage on N type, well, I'm going to write subscript VGSN, is now VDD. On QN, we have the voltage VDD. Now the current is same, which should be flowing. So if I may write, I is supposed to be equal to IDP, which should be equal to IDN. Now in this case, as the voltage at between the source and gate of QP, which you can write VSGP, that is 0 because VDD is applied here at the input and VDD is the power supply. So hence the differential between these two is 0. So gate to source for the PMOS is 0. So which means then this guy is it has to have so which means it's less than the threshold voltage, so there is no current. It's an open circuit on this side, so which would mean that the current is 0, if I may write it here. But there are implications about this, that what's going to happen in this situation. I can write an equivalent circuit where we can show that on the PMOS there is an open circuit, and we always have small resistance, and that resistance is the same that we calculated before, which is RDS for 1 over a whole factor for VDS small case. And that resistance is what will give us the small resistance on the output. So So there is a very small resistance, so you can say there is voltage drop, and that's what leads us to that the margin on the input and output that still is considered as high or low up to certain output voltage. Now, the for this situation, the curve, if you look at the load, we have to look at both of these gates and see what is their load line. So if we draw the load line for the first situation, we see that for the PMOS, the load line is nothing but a straight line at zero. So all the way to VDD, it's there's no current. There's no current flowing. But for the load line for the NMOS is what we can see that it starts in triode region and gets into saturation, the standard curve, so that drain and VDS curve for QN shows us a value, and this is the point where both intersect. So if you think about it, this is where there is maximum rate of change, so maximum slope for the NMOS. So the operating point is then at a point where there is a zero current, hence we see that there is ID is zero, but this operating point tells us that the intersection of two curves where the output voltage zero and current through devices is also zero. Now, when the current is zero, the power dissipation is also zero. So, power dissipation is zero, which means that the result that we get at the output for high input results with zero power loss. So, inverter is acting just as an inverter and not contributing any power or taking any power away from the signal. Now, in a similar way, when the input is low, in this case, our QN has voltage at gate 0, which means it's open circuit, but the voltage on the source and gate for P type is now VDD. So that's now short circuit, but there's no place for the current to go. So current is again 0, and our output is now what shows up from here to here. So our output is now equal to VDD. Now in this case again, we can draw the circuit with the load lines, and the graphical representation of the operating point for this case is similar to what we saw for the input, low input. So for the high input, so low input is the same. Now in this case, the extreme where the input is 0, we see that the QN is operating at 0 gate voltage. So for it, the characteristic is a horizontal straight line at 0 current level. But for the load curve for ID VST, we are superimposing that, so we have to follow the direction of the voltage. So that's why it's reverse for P type. So we see that intersects at this point, and that point is when the source to which is the starting input, which is supposed to be high. So and that goes all the way up to the power supply. So this is the intersecting point. So here again, the current is 0. This is open circuit, so there is no current that's flowing. And again, there is 0 power dissipation. And so we can see that in both extreme cases, the power dissipation is zero. For this case, again, now this was the resistance for the N type, the resistance for the P type is the same, but only difference is that we are using the plus value of the threshold voltage against outside the P type transistor. Now, here are some important things from this. The equivalent circuit shows that the output is always VDD and the power dissipation is zero. So we can easily see few things. One is that the load driving capability of inverter is high, which means that as soon as we provide an input, we get change on the output. So we can sync when we are grounding the load, we can sync it to, we can take the current, ground the current, so we can drive the load pretty heavily. And if there is any capacitor, for example, we can discharge it really fast in that case. So which means that it can have a big impact on it can drive the load in a very decent way. So if I clean up the whole thing, so we can see here the effect of this guy is to bring the voltage down and draw the current in. And that's why we call it, so it's sinking the load current and pulling the output voltage down towards ground. So that's why we call these as pull down devices. So in a similar way, when the input is low, the transistor QP can cause a relatively large load current. So which means then it can provide high current and can result into charging of maybe if there is a capacitor on the load, it can, so then it can pull the output voltage up and try to bring it towards the power supply. So hence we call them the pull up device. And we have seen this idea. So in the case of an ideal inverter, then there are a few observations which are important for us. And these observations conclude the basic CMOS logic inverter behavior. First is that the output voltages will be between 0 and the power supply. So, and the signal swing is the maximum possible. And if we recall, we want that signal transition to be really fast with infinite slope, infinite gain. So from high to low, that's the signal swing which is maximum possible. So we can now with QP and QN, it's possible that we can design to have a symmetrical voltage transfer and thus have wide noise margins. So that's also something which we saw, that VOL and VOH idea, that how far can they go on the output side and still be considered as a high signal or low signal. We'll look at that in a moment. That's one thing. The other important thing we see that there is very low static power loss, very almost zero, and that is, if we want to quantify, we can find that from the resistance through the drain source for N type or the resistance for P type DSP. So we could find those resistance, but we just ignore that. We ignore the leakage currents also. So for the simple reason, there is no DC path between the power supply and ground in either high input or low input. The third observation is there is a very low resistance path between the output terminal and ground. So that's three. Number two is power, no zero power dissipation. Zero power loss. So very small, very low resistance between the output terminal and ground, and they ensure that this low resistance ensure the output voltage zero or VDD independent of the exact values of the device physical characteristics, width over L, or other parameters. The small resistance also make sure that there is least effect of noises or other disturbances on the output. And number four is that this pull up devices and pull down devices, what we call pull up network and pull down networks, they provide high output driving capability in both directions. So they can drain current from the output or they can supply current to the output. And the last point is that there is infinite input resistance to the inverter because there's no current that flows through the gate, and gate is where we supply the input. So there's no direct flow of current. So we have infinite input resistance to this circuit. So which means that the inverter can drive large number of similar inverters with no loss in signal level. So your input can be provided to bunch of inverters because there's no power loss happening because that it's infinite input resistance. So you have many inverters that can be driven. However, for each there are other issues which are more to do with their switching behavior and their switching times. Now, what are the voltage transfer characteristics for a CMOS inverter like we just saw? So we have to look at what are their threshold dependence and what is their size dependence and see that what are the voltage transfer characteristics on both sides at high input and low input, and how does the output high and output low change with that. Now, before we get into that, this is just recap of the drain currents that we already know. How do we calculate for in case of triode or in case of saturation for N-type? These are the equations that we use to find the drain current. In a similar way for a PMOS, in the situation of triode or in situation of saturation, again how we find out the current. So we have seen how to drive that, but here we will take use of these and see what would be the effect on the voltage transfer characteristics. So in case of a QN and QP like we saw coming together, there are a few things that we need to understand to have the same behavior in for any output, to achieve any output for any given input. We have to look at their individual characteristics and see if they match. If they match, which means their behavior will be exactly the same. But there are fundamental differences, and those differences stem from this factor what we call Kn prime, and the simple reason is that there is a dependence on mobility for both devices. So when we talk about mobility, we are then talking about their transfer characteristics. So if we consider them to be matched, we design them in a way that their threshold voltages are the same, so we can just call it VT, which is not always the case, but that's achievable. But for that, they both have to be matched. To match them, it means that their transfer characteristics will be same. But the problem is that mu n and mu p are not equal. In fact, mobility of electrons is much more higher than mobility of holes, and almost to one, almost double or four times, which means that to bring the mobility of holes to mobility of neutrons, to mobility of electrons, we will have to make the width of p channel device much bigger, so as much as 2 times to 4 times, while keeping the length small, because length is the characteristic which defines the channel length for any given technology node. But the width can be made larger to achieve this condition, that we want to have them to be matching with each other and to have this situation satisfied. So from this, we can get this satisfied. And if we get that, then we would get symmetric transfer characteristics for both, and they both will have equal current driving capabilities in both direction, whether it's pulled up or pulled down. Now, if we achieve that, we can then see there are 5 distinct segments in different modes of operation of a transistor. And this builds up on the non-ideal situation that we saw, that when we switch the output from when we switch input from extreme zero, low to high, how does the input change? And then we said that in ideal transistors we want this to be really steep, which is indeed the case when we look at the voltage transfer characteristics of the CMOS inverter that's made with the PMOS and NMOS. So here there are 5 interesting segments, and what we see here is there are different combinations of the mode of with the mode of operations of PMOS and NMOS. So this part BC is where the transition happens at the point where QN and QP are both operating the saturation region. And in the saturation, we neglect the finite output resistance. That means that we can assume there is no channel dependence, and hence the gain is infinite. The slope is infinite, and we can say the gain is infinite. So this vertical segment, we can, if we take a look at it, we say this occurs at halfway of the input voltage, and we can say this is where the input voltage is half of VDD. So if this is VDD, this is happening at the right in the middle. So we can write VI is equal to VDD by 2. That's the midpoint where it occurs. We'll come to voice the margin of noise later on. But this vertical segment is bounded by the output here that occurs at this point, and the output that occurs at this point. So the input is at this point, but the output is bounded by these two values. So hence VDD by 2 plus VT, and VDD divided by 2 minus VT. So hence we can see that we are going from QP operating towards Q1 operating and vice versa. So at this point, QP enters in the triad region, while we could say that Q1 is also entering the triad region, depending on whichever way we are going. Now, we can think that in addition to the these 2 points for VOL and VOH on the output side. There are noise margins from here, and we had an arbitrary number, but now we have this. The input has a boundary of up to which point it will be considered as low, and then high has a boundary as up to which point it will be considered as high. So if we take a look at that, so these 2 points determine the noise margin of the inverter. But if you look at it, interesting, those are the points where the slope is 1/1 minus 1/1. So that's the just before we get into the infinite gain. Now these are 2 points on the transfer curve where the incremental gate is unity, and beyond that the gain becomes infinite. So let me just clean up. And these are on both sides, there are these areas which we are interested in, want to calculate. Now, how do we find out what is the margin of noise? And we can take the equations of currents, because at these points we can see when QP is in saturation, and that has this current IDP, and QN is in triode. So that's the point where it happens. So we can take both these currents and we can equate them. So going back to these current equations, we can take the for QP in saturation and QN in triode, we can equate them, and that would give us a simple clean relationship for noise margin and the levels of these two as well as the noise margin. So after playing with equating these two equations, we get VIH equals 1/8 times 5 VDD minus 2 VT. So in a similar way, we can also find the boundary of the noise margin, which would be 1/8 times 3 VDD, 3 times plus 2 times of threshold voltage. So these two equations for the matched QN and QP tell us that what is how far can it go, how far an input will be taken as low before we get the switch on the inverter output. Similar way, how small will be the input going down, after which the output will switch. So from these, then we can find out exactly what is the noise margin for this CMOS, and that is we discussed that this is the difference of these two. So that's the difference between the output, high output, and high VOH minus VIH. That's the difference between these two is what will give us the noise margin, and that we can find from the difference of these two, VOH minus VIL, and that comes out to be 1 by 1 by 8 times 3 times power supply plus 2 VT, twice the threshold voltage. In similar way, there's the on the lower side, this is on the high side. Similar way, we can find the noise margin for the lower side, which would be VIL minus VOL, and that's the same as this guy, which is expected because it's the symmetry. So we have equal noise margins on the lower side and the high side, which is essentially a feature of the QN and QP. So this is situation when they are matched. But as I said before, this is not always easy, because if you make our PMOS too large, we are wasting lots of space on our chip. So which is not just the that we don't have in too much real estate on our chip, but bigger device would cause more capacitive interference. So it's not always the case that we can match them. So there are situations where then we have to know that because of mismatch, how much is uh, the noise margin, and what would be the difference because of the difference in the mobility. So R is the factor then that dictates the noise margin because of the mismatch between the PMOS and NMOS. And this is something which we define in terms of this function R, which is the ratio of the square root of the ratio of the transfer characteristics. And for any given process where we know the power supply threshold voltage for N-type, threshold for P, we can find out the noise margin. For example, for 65 nanometer technology, the noise margin is its dependence with R can be seen here. So there are a couple of observations. You can see that it increases with R, which means that uh, when the transfer function of positive of the PMOS is higher than the NMOS, it shifts VM more towards higher value close to VDD, and the other way it will go down. As we can see, smaller R will bring it down away from VDD towards zero. So noise margin will be smaller if we have transfer characteristics width smaller for PMOS. Another important observation is that it's not a very strong function of R. What we are saying is that going from two orders from 1 to 0.5, making it half does not change the noise margin too far. It just changes by 0.05 in that direction. So there is it's always, we can see that the the switching voltage where we go from high to low then has a dependence on the device size, and it can be slightly uh, moving from the midway point to up or down depending on the R value.